All right, welcome everyone to the next seminar. I'm very excited today because we have Nicolas Martini, who's coming to us virtually from France, from Lyon. So Nicolas is a PhD student who is working on a very interesting upcoming experiment called Ricochet, which is seeking to measure coherent elastic neutrino nuclear scattering with reactor neutrinos. So this is quite an exciting experiment. So I invited Nicolas to come and tell us about it. So thanks very much for waking up early to be with us, and I will hand over to you. Thank you.
Hello, everyone, and thanks, Kieran, for the invitation and a nice introduction. So I'm going to talk about studying CEvNS with the Ricochet experiment, which is the experiment I'm part of. And you can see a photo of some of the members of the collaboration on this slide. So this presentation will be divided in three main parts, which in the first part, I will talk about the physics of CEvNS and a little bit of state of the art of its current study. Then I'll talk in more details about the Ricochet experiment and the ideas behind it. And finally, I'll give a current status of the Ricochet experiment, and I'll present some of the latest results that we've obtained. So let's get into it with this first part on the physics of CEvNS, which stands for Coherent Elastic Neutrino-Nucleus Scattering. So let's dissect a little bit that name. We are talking about an interaction between a neutrino and a nucleus, more precisely a neutrino scattering of a nucleus. It's elastic because at the beginning and at the end of the interaction, we have the same components, hence a neutrino and a nucleus. And the coherent part comes from the fact that the neutrino interacts with the entirety of the nucleus and not one of its components. It can see protons or neutrons or even quarks. It scatters off of the entire neutrino. So here already I have to make a little bit of a disclaimer. Since I am a French speaker, in France we usually say sense with two N's for neutrino and nucleus, and English speaker usually say CEvNS with a V for the neutrino, so I might make a mistake. I'll try not to, but if I say sense, know that it's the same thing as CEvNS. So in our detectors, this interaction translates like this. We have a neutrino, it scatters off of the nucleus of an atom, it deposits some energy that we call recoil energy, and it creates what we call a nuclear recoil. Neutrinos aren't the only particles that can create nuclear recoils in our detectors. Neutrons can create nuclear recoils too, for example. And we can also have another kind of events in our target mass, which are electronic recoils, which is when a particle, for example, a photon, scatters off of the electrons of our atoms. This interaction in the standard model, it's very well described by the exchange of a Z0 boson between the neutrino and the nucleus. And as you can see at the bottom left of this slide, we have an equation for the cross-section, in this case more precisely the differential cross-section of this interaction. And in this equation, we can see some interesting terms, starting with the F term here, which is the form factor. Which is an image of the coherency of the interaction. If you are at higher energies of incoming neutrino, this neutrino will be able to probe the insides of the atom and its components, and the interaction will be less coherent. This factor will go below 1, and in the case of a low energy event, a fully coherent CEvNS event, this factor will be at 1 and it won't perturbate the other members of the equation. Another interesting factor is this QW factor for the weak hypercharge, and it tells us that this interaction scales with the number of neutrons in our detectors. But it also tells us that this equation depends on theta W for the Weinberg angle. And here already we have one of the interesting reasons of studying CEvNS, and it's because its study can bring us more knowledge about specifically the low energy values of theta W, which aren't very well constrained by experimental data as of today. And here I also added a little bit of text from the original paper of Friedman in 1974, in which he first described this process. And as you can see, he said that his suggestion might be an act of hubris because of the inevitable constraint of interaction rate, resolution, and background, which pose grave experimental difficulties for the studies of this particular interaction. And this sums up why we had to wait up until 2017 for the first detection of this interaction. And I also have to note that I originally come from a group that historically has been studying dark matter. And the question is, why do people that are studying dark matter are interested in CEvNS? Well, here we have a plot from Kieran, who has invited me here, which explains it quite well. We have in the green part the different limits of dark matter direct detection search experiments. And in the blue part, we have what we call the neutrino fog, which shows the density of CEvNS events that could happen in the dark matter detectors. So if you're improving your dark matter experiment, this green region will go down, and at some point it will overlap with the blue region, and you won't be able to tell if the events that you're seeing in your detectors are potential dark matter candidates, or if we are just seeing CEvNS events. Which means that at some point, direct detection search of dark matter will be limited by our knowledge of CEvNS. In this created phenomenon, which is that some direct detection dark matter experiment created some spin-offs for CEvNS study. Of course, there's not just dark matter experiments that are looking at CEvNS. It is here you have a little map of the different experiments that are studying CEvNS throughout the world. Of course, I won't be able to talk about all of them, but there's quite a few that I need to mention. So I will classify them by their neutrino sources, looking at reactor neutrinos and accelerator neutrinos. So I'll start with accelerator neutrinos. So as you can see on this slide, the energies of these neutrinos are of a quite wide range and are at quite high energy, which makes them easier to detect and specifically interesting for nuclear physics. Because as I said, if you are at high energy, you are at low coherency, which is shown by this red arrow on this graph, which means that you can probe the components of the nucleus, and this is of course very, very, very interesting for nuclear physics. And the fact that it's at high energy explains why the first detection of CEvNS was done by an accelerator neutrino experiment, which is Coherent, which had its first detection of CEvNS at the Oak Ridge Spallation neutron source in 2017. So the idea of this experiment is that they use a proton beam and they are shooting protons towards a specific atomic target. From the collisions, pions are created. These pions decay, and in this decay, they are creating quite a few neutrinos, which travel towards the different detectors of the Coherent experiment, which are regrouped in what they call the neutrino alley at the Oak Ridge Spallation neutron source. And the fact that it's quite high energy and that they are capable of knowing exactly when the neutrinos are arriving to their detectors help them to get the first detections, first on cesium iodine in 2017, then on argon in 2020, and quite earlier this year on germanium. And the fact that they were able to detect it on three different targets is extremely important to study the n-square dependence of this interaction. And the fact that it's at quite energy makes it very sensitive to form factors, and as I said, very interesting for nuclear physics. But they can also do a little bit of beyond standard model physics with studying NSI and light mediators, for example. But if you want to look at beyond standard physics, model physics, well, it's not the right way to go. Because the right way to go is to look at reactor neutrinos. So as you can see, they have quite a lower energy range corresponding to the red spectrum here, and which makes them, of course, less sensitive to form factors. But it turns out that it makes them more sensitive to potential beyond standard model physics, as I will be able to show very soon. In terms of reactor neutrinos experiments, there are quite a few that I need to mention. First, it's important to mention CEvNS from the Brockdorf reactors in Germany, which has proven to be to a factor 2 from the expected 7 signal in quite recent analysis. And they are moving to Switzerland with the CONUS Plus experiment at the Leibstadt reactor. The other experiment that is important to mention is the Dresden 2 experiment, which has recently claimed another 3 sigma detection of the 7th signal, but to be honest, it's quite highly controversial in the field right now. And finally, we can also mention the NuGen experiment, which has proven to have a factor of a few, to be at a factor of a few from the 7th signal. And one common point between all of these experiments is the detector that they're using. They're using HPGE PPC for P-type point contact high purity germanium detectors, which are ionization reading detectors trying to measure the ionization deposited in the crystal by the 7th elements. And these detectors are operated at around 70 kelvins. But turns out that there's another way to try to look at 7th events, and it's not to look at the ionization they produce, but at the heat they produce. And to do that, you might want to get at a lower temperature than 70 kelvins. You want to get as low as possible. And it turns out that this is what some direct detection dark matter experiment, more precisely cryogenic targets experiment, had been doing for quite some time, which explains why they created some dark matter, some 7th spin-offs. And in this vein, Edelweiss created the Ricochet experiment, Super CEvNS created the Minor experiment, and Quest created Nucleus. And here we can see why it's so interesting to go at lower energies for studying reactor 7s, because we have here a graph of the event rate in our detectors in function of the recoil energy of the events. And here for the reactor at ALL in the Ricochet experiment, we have the prediction of the standard model in blue for the spectrum. And in dotted lines, we have the prediction for different beyond standard model theories. And as you can see, the lower you go in energies, the more interesting it gets, because you are more capable of distinguishing the different theory prediction from different theories. But this is just prediction for recoil energy. But when you're building an experiment, you encounter some other challenges. The first one is that your detectors aren't perfect and they don't have a 0 electron volt threshold. So in our case, in the Ricochet experiment, for an illustration, we have a goal of 50 electron volt threshold, which is represented by this red vertical line, which means that anything that happens on the left of this line, so below 50 electron volts, we will never be able to see. And another thing that is quite challenging for this kind of experiment is background noises, because we don't just have neutrinos in our detectors. In fact, we have other kinds of particles, for example, neutrons that can create nuclear recoils, and we have other particles that can create electronic recoils. And these levels represented are when the background noises are the expected background noises in the Ricochet experiments, and they can mask our signal. And here you can already understand the importance of being able to discriminate between electronic recoils and nuclear recoils, because if we are capable of doing that, we can access to the light gray region, which contains a significant portion of the standard model prediction. So let's get to the next part of this presentation about the Ricochet experiment and the ideas behind it. So the Ricochet experiment is a collaboration between France, the US, Canada, and Russia, which now accounts for a little bit more than 60 members. And we aim at building a low-energy neutrino observatory in order to measure with high precision the CEvNS process. And to do that, we count on two different detector technologies. The first one, which is the QOA, which I will not be talking about a lot in this presentation because it is still quite at an R&D stage, and it's clearly not as mature as the other detector technology, which is the cryocube one, which I will talk about in more detail, which will be the main focus of this presentation. So if you want to detect CEvNS with the Ricochet experiment, what do you need? Okay, so first you need a neutrino source, which we find at the nuclear reactor at Institut Louis-Langevin, ILL, in Grenoble. And you want to get as many neutrinos as possible from this neutrino source, so you are getting your experiment as close as possible. And in our case, we are installing our experiment at 8.8 meters from the center of the reactor core. Then you have neutrinos, you need to detect them, and to do that we use, as I said, the cryocube, which is composed of 18 germanium bolometers. And as I mentioned, we are trying to detect the heat produced by these neutrinos in our detectors. And the lower the signal you want to look at is, the more interested you are in getting at very low temperature to have a low baseline for your small signal. And this is why we are using a cryostat that brings us to about 10 millikelvin. And once you have all of that, you still need to take care of the different background noises that can happen in your detectors. And these background noises can have a few different origins. So they can be cosmogenics, coming from the sky above us. They can be reactogenics, coming from the reactor that is operated at 10 meters from us. And they can even be radiogenic, so coming from the radioactivity of the component itself of your experiment themselves. And to deal with these different background noises, we have different shielding strategies. We are using a muon veto to tag the muons that we will never be able to stop anyway. We are using 20 tons of lead to deal with the different gammas that might come into our detectors. We are using 4 tons of polyethylene, and more precisely of borated polyethylene, to deal with the neutrons. And the facility provides us with a water channel, which grants us with 15 meter water equivalent of overburden, which is extremely useful to diminish the cosmogenic backgrounds. And on this slide, you can already see a photo of the installation of the shielding in March 2023 on site. And you can see a CAD file of the experiment with the cryostat in the middle, the detectors at the bottom of the cryostat, the white part corresponding to polyethylene, the black part corresponding to lead. In red, we have the muon veto, and in blue, we have the structures that are holding the cryostat in place. And everything is installed at ILL H7 reactor site. We have a plan of it on this slide. Here we have the reactor core, and in blue it's the place in which the experiment is installed at 8.8 meters from the center of the reactor core. And this proximity, along with the 58 megawatts of nominal thermal power of this reactor core, it should give us about 11 CEvNS per day and per kilograms of target mass if we reach a goal of 50 electron volts of energy threshold. On top of that, as I said, the facility provides us with 15 meter water equivalent of overburden, and it also gives us 3 to 4 cycles per year of the reactor going on and off, which is extremely important to be able to understand if the backgrounds that you're measuring come from the activity of the reactor or not, and to be able to subtract any uncorrelated background. On the topic of backgrounds, I can mention that there was a paper that was published in 2023, which was studying specifically that, and the results of this paper taught us that the reactogenic neutrons in our experiment should be negligible, and that we should be able to reach a signal over background ratio of about 1. But before talking about either signal or background, we need detectors. So let's dive a little bit deeper into how they're working. So these are the red detectors inherited from the Edelweiss experiment. And the idea behind these detectors is that we have quite high purity germanium crystal in which some particles are scattering off of the atoms of germanium. And when a particle scatters off of an atom, it creates some phonons. It creates some phonons that will thermalize into heat, which can be detected by a heat sensor placed on the top of the crystal. And another thing that happens when when a particle interacts with an atom of the crystal is that it creates electron-hole pairs, which with the help of electrodes on top and the bottom of the crystal, we can apply a bias in our detector and we can make them drift to be collected at the electrodes. Which means that we can measure heat and ionization of the recoil energy of the events. And this dual measurement of the recoil energy is at the heart of the particle identification idea in our detectors. Because if you look at the ionization energy divided by the recoil energy of your events, what we call the ionization yield or the quenching factor. Well, different events give you different ionization yields. For electronic recoils, you get an ionization yield of 1. For nuclear recoils, you get a quenching of about 0.3, following the Lindart model, which I will talk about a little bit more right after. And you can even see some heat-only events, which don't produce any ionization. Some experiments that don't measure experiments call them low energy excess because they are rising exponentially at low energies. And to be honest, we have no idea what these events are. They weren't expected by the first person who created cryogenic targets. There are some ideas that there may be some micro cracks in the crystal that are rearranging and dissipating some energy into our crystal while we are taking data. But we have clearly no idea of what they really are. And anyone who is using cryogenic targets detectors should be able to take care of that. Should be prepared to take care of that at least. And this kind of detectors, it grants us with the kind of plot that you are seeing on the right side of this slide, which is for a performance plot from the Edelweiss 3 experiment. In this plot, we can see the ionization energy of the events in our detectors in function of their recoil energy, and you can see multiple populations. So in red, we have electronic recoils with two interesting features, which are our calibration peaks, which is the electron capture of germanium-71 in our crystal, which produce peaks at 1.3 and 10.37 keV. And then in red, you have the nuclear recoils in our detectors, here produced by an Americium beryllium source next to our detectors. And the whole goal of improving your detectors is to get these different features to get as small as possible and as thin as possible to be able to distinguish them better. Another goal is to get this used mass at the bottom, which is our electronic noise, to go as low as possible to be able to probe lower energies. So I mentioned that we have quenching factors, and for nuclear recoils, it follows the Lindart model. So the Lindart model on this plot of the ionization yield in function of the nuclear recoil energies is represented by the blue line. In fact, on this graph, we have quite a few different lines which correspond to certain models, and we have quite a few dots corresponding to some measurements. But as you can see, we don't have a lot of measurements at low energy, and we have even fewer measurements if we look at low temperatures. And it turns out that the ones that we have are not in agreement either with each other or with the theory, which is quite problematic, because this means if we follow at least the Lindart model, that at low energies, we have an ionization yield which is quite low. And as I mentioned, heat-only events, it could mean that it's really hard to distinguish a nuclear recoil at low energy from a heat-only event. And the fact that we don't know who to trust could be problematic. But in the case of the Ricochet experiment, from the fact that we are able of measuring the ionization and the heat produced by the CEvNS, we will be able to measure our own quenching factor. Another interesting thing about the Ricochet experiment and its detectors is the electrodes design, because we have two of them, planar and FID. So first, we have a planar design, which is just two very plain plain electrodes on top and on the bottom of the crystal, which help us to have a very homogeneous field, which grants us with a very huge usable volumes or fiducial volume. But it doesn't help us to reject surface events. And from experience, we know that by operating these detectors, these can be quite of a hassle. And this is the reason why we have another electrode design for these detectors, which is the FID1, this time not with plain electrodes, but with rings of electrodes, which are at different potential, which help us to create a more complex field in our crystal to be able to detect if an event is close to the surface or not. So this grants us some surface event rejection, but it comes at the cost of a substantial part of our fiducial volume. And finally, we can install these detectors 3x3 in what we call the mini cryocube, which is a design that you can see on this slide. So I could talk about this design for quite a long time, but I would like to bring your attention on one specific feature of this design. So detectors, they have a quite low intrinsic capacitance, which in terms of ionization measurement means that we are dominated by the parasitic capacitance of our acquisition electronics. So if you want to improve your ionization performances, you might want to bring an amplifier as close as possible to your source of signal, to your detectors, to be able to amplify your signal before the noise added, for example, by the cabling injects into your data. And this is what we are doing with this design by bringing our amped preamplifiers directly on the top stage of the mini cryocube, which is at 1 Kelvin, which is the operating temperature of these amplifiers. And which is only at 5 centimeters from the bottom stage, which is at 10 millikelvin, and which is hosting the detectors. And this is possible with the help of these Z and X PCs, which are made of what we call T-metal, which is a titanium alloy, which has very low heat conductance, but very interesting mechanical properties. And these mini cryocubes, we can regroup them in what we call the cryocube, which is our final detector, and which is composed of 2 levels with 3 mini cryocubes per levels, which in the end means that we have an array of 18 times 48 of 18 bolometers of 48 grams, all cooled down at 10 millikelvins. And if we reach the goals in terms of performances for the cryocube, which are to get 20 electron volts in heat and ionization resolution, and to get timing resolution of about 100 microseconds at 100 electron volts, we will have a detector which consists of 680 grams of payload, divided into 2 detector technologies, planar and FID, which we can choose from at any time, to be able to achieve particle identification down to a few tens of electron volts with a rejection factor or above 1000. And speaking about the performances of the mini cryocubes, we have published a paper earlier this year on the ionization performances, in which we were able to demonstrate a 30 electron volts ionization resolution. So it's time for me to get into the third and last part of this presentation, which is the Ricochet status and result, which is quite frankly an occasion for me to show you some nice photos of the setup. So let's get into it. So this little story starts when we received the Ricochet cryostat in Lyon at IP2I in my lab. that we were able to install properly. And during this commissioning phase that started at IP2I, we were able to operate one full mini Query cube with its Ricochet dedicated electronics inside the shielding at IP2I, which is composed of 10 tons of lead and 1.5 tons of polyethylene. And after, as you can guess, but the number of the runs here, after 9 purely cryogenic runs, we were finally able to be sure that the cryostat was giving us the cryogenic properties that we expected of it. After that, we were finally able to get our first 2 detector runs in the Ricochet cryostat in July and September 2023. And from these detector runs, we were able to acquire some data, and it produced the plots that you are seeing right now. So this is a comparison between the Edelweiss plot, that performance plot that I presented earlier, and the Ricochet plot at IP2I. And as you can see, we have improved at our electron recoil, nuclear recoil discrimination threshold by about 1 order of magnitude with respect to Edelweiss, which was our starting point in terms of R&D before getting into the Ricochet experiment. And our energy threshold have improved from 4.5 keV to 300 electron volts. Our ionization threshold from 700 electron volts to 160 electron volts, which means that our heat and ionization resolution are now about a factor of 2 from the Ricochet final goals. And if you look at the region circled in blue, this also means that Ricochet is now capable of probing reactor neutrinos with highly efficient low energy excess and electronic recoil rejection. And to us, this was the signal that we had the green light to go at ILL. So it's what we did, of course. As you might remember, the outer shielding was already installed at ILL in March 2023, and it's composed of 20 centimeters of lead for gammas, 35 centimeters of polyethylene for neutrons, and some soft iron for to create a magnetic shield to deal with all the magnetic perturbations that could be brought to our experiment, for example, by other experiments in the ILL. And we were finally able to install this cryostat from November 2023 to February 2024 on site. Which means that we could start the 12th run of the Ricochet cryostat in February 2024, which is a purely cryogenic run in which we were able to validate that we would get a minimum temperature without payload of 8.6 millikelvin, which is exactly what we aimed for. Cryogenics are validated, so of course now we are putting detectors in the cryostat. This started in the 113 in February to April 2024, which was our first detector data taking on site. And we were capable in this one to acquire more than 1,000 hours of data on 2 different detectors while testing some simultaneous data taking. And we were also able to look at our data when the reactor is on or when the reactor is off. This was all done without internal shielding, so of course we wouldn't be able to see any neutrinos even when the reactor is on, because without internal shielding you will have way too many neutrons to see any other kind of nuclear recoils. Another thing that we've been able to test in this 13th run of the Ricochet cryostat are our different vibration mitigation strategies. So you're operating your experience 10 meters away from a running nuclear reactor, which means that there are quite a lot of things that are vibrating, and you don't want this vibration to get to your detectors because it will of course decrease your heat performances, but in truth it will also decrease your ionization performances. So to deal with that, we had quite a few strategies. The first one is the use of 2 different frames, which is called UQT to hold the cryostat, UQT for ultra quiet technology. And it's a true frame that you can see on this photograph with the interior frame, the interior frame that is holding the cryogenic stages and decoupling them from the rest of the installation. Then we have been testing the use of damping pads that you also can see on this photograph in brown here, which are decoupling this lower stage, which is holding the cryogenic stages of the cryostat. decouple them from the floor, of course, which is vibrating. And finally, there's a third frame that has been installed to host the water valve and ballast of the cryogenics, which are the most vibrating parts of the cryogenics, but this has only been tested in the next one, which is the 14th one. And as I mentioned, we were able to take some data. So let's look at what we've obtained. Here it's a first in situ detector performance assessment of our experiment. And you can see spectra of the ionization energy in our detectors and of the heat energy of the events in our detectors. More precisely, only of the electronic recoils that happen in our detectors. And you can see here the peaks that I mentioned before of the L shell and K shell electron capture of germanium-71, which produce peaks at 1.3 and 10.37 kV. And as you can see, we have quite nice peaks, and we got a baseline resolution of 40 to 45 electron volts in ionization and 35 to 40 electron volts in heat. But the question is, this is all data taken when the reactor is down, so is off. So what happens when the reactor goes on? Well, here is the same plots when the reactor is on, and as you can see, we have quite similar performances. And in terms of resolution, we went from 40-45 in ionization to 45-47. And in heat, we even went from 30-35 to 25-27. So this might seem a little strange, but this is perfectly explainable because the reactor off data that I shown previously had been taken quite early after cool down, which means that our detector most certainly weren't at their lowest temperature, and they had the time to cool down before we took the reactor on data. Of course, this meant next step 114, which has been called and taking data since May 2024, which is a great accomplishment for us. I will explain why. The goal of this specific one is to characterize backgrounds with full shielding and improve vibration levels to be able to produce as soon as possible a first data-driven 7th sensitivity. So I mentioned that in this one, what we added, the most important thing that we added is the full shielding, and more precisely the inner shielding, which you can see photos of in this slide. It's composed of polyethylene screens in between the cryogenic stages of our cryostat and of stacks of lead, copper, and polyethylene to close the opening made by the cryostat in the outer shielding. But the addition of this inner shielding means that to cool everything down at 1 Kelvin, you need 10.5 days, which means that once you cool down, you very much hope that you don't have to warm up very soon. Hence the reason that we are quite happy to be able to be cold and taking data since May 2024 up to now. There's another interesting thing that I can mention about this 114 of the Ricochet cryostat, and it's the test of a new idea in terms of detector calibration and charge trap neutralization. So in terms of detector calibration, as I mentioned before, we are using the 10.37 and 1.3 kV peak from germanium-71 electron capture. But these peaks, their activity tends to go down with time, and at some point you might not be able to see them anymore. So if you still want to be able to calibrate your detectors, you might want to have another source of calibration. And to do that, one way to do it is to bring optical fibers to your detector and to shoot with a laser some very short pulses directly on your crystals to be able to calibrate your data. And in terms of charge trap neutralization, well, we are operating our crystals at a certain bias, and after quite some time and quite a certain number of events in our detectors, well, it creates some charge traps which degrades our ionization collection. And one thing you might want to do to improve your ionization performances is to shake all of these charge traps to get them in a better state. And you can do that also with the laser by just bombarding your crystal with a huge number of photons for a short period of time to get everything to be in its original place. And another thing that I haven't mentioned in the experiment, but which is quite important when we are talking about this kind of experiment, any experiment truly, is the way you handle your data. So this is the QueryCube data flowchart. I won't comment on everything in this flowchart, of course, but I just want to mention that there are three main parts. First, an acquisition part, then a processing part with a specific library, software library, which is called MPS, and an analysis part with another specific library, which is called BART. And what I want to mention is that these whole structures and all the libraries that are used and all the software that are used have been developed by the collaboration for the use of the collaboration. And everything is up and running and perfectly usable by the entire collaboration as of now, which is a huge step towards the production of interesting papers. In terms of next steps to complete the Ricochet commissioning at ILL, and more specifically the Ricochet background mitigation strategies, we still have to validate our muon veto and synchronization. So we are taking data on quite a certain number of detectors, and we want to synchronize them with muon veto systems, which means that you have to give a common clock to all your acquisition cards and your veto systems. And this can be done through the help of this synchronization board that you can see on this slide. This has been in test for quite a few months now and is near its completion and validation. And then, as I mentioned, muon veto systems. We have two different muon veto systems in this experiment. A cryogenic muon veto system, which is cooled down at 4 Kelvin inside the cryostat, and an outer muon veto system, which is composed of two-layered scintillators. Their installation are now completed, and the analysis of the first data from the outer muon veto to validate them is in progress and should be done quite soon. So to summarize this ongoing commissioning, I can talk a little bit about this plot of the mixing chamber temperature of our cryostat where our detectors are placed through time since February 2024. And we can see that we started with 112 and the validation of the cryogenics, which we got a base temperature of 8.6 millikelvins without payload. And then we went to the 114, in which we did some detector performance assessment with the reactor going on and off, and we were able to test our different vibration mitigation strategies. And finally, since May 2024, we are in the 114, which objective is to assess, to characterize the backgrounds in our experiment with full shielding this time. And in terms of future prospects for the experiment, by the end of 2024, we should be able to finalize of our ATER and cryogenic muon veto installation and to validate that everything is working well. Then we should be able to commission the readout electronics and synchronization board to finally be able to produce a first data-driven 7 sensitivity estimation from this commissioning phase. Then the idea by the end of spring 2025, the idea is to complete the full QueryCube payload with its dedicated electronics, which will mark the start of the Ricochet QueryCube neutrinos science phase, which will consist for the next 2 years in 2025 and 2026 to accumulate 7 on and off reactor cycles to achieve our nominal exposure, the nominal exposure that we aim at. And I would like to end this presentation by thanking everyone for listening to me. And if you are interested in Reactor 7 neutrinos and in the results of Ricochet, I would encourage you to stay tuned because we are taking data and we have results that are coming out quite soon.
Thank you very much. Any questions? Bruce?
So, Nicolas, thanks for the talk. That was all very interesting. You mentioned early on that you have the capacity to measure the quenching factor in-house within the experiment, but you didn't speak to
Yes.
that in detail during the talk. Do you want to expand on that a little?
Yeah, I can expand on that, of course. So when you want to do a quenching measurement, the idea is to have quite a lot of neutrons and to be able to measure their ionization of nuclear recoils, so neutrons in our case, and you want to measure their ionization energy in function of their heat energy to be able to tell at which quenching they are. And since we are capable with this detector to measure heat and ionization at quite a low energy, we will be able to produce a lot of neutrons with a neutron source in our detectors and create this kind of neutron calibration, from which we will be able to fit the quenching factor in our detectors.
But how is that going to be accomplished? Is there going to be some sort of neutron transport line? Is there a movable source you can introduce while that's under cryogenic conditions? The practicalities seem not
so
trivial.
when you have a nuclear reactor next to you, it's quite easy. You just have to open your shielding a little bit, and there's quite a lot of neutrons that are going to get into your detector.
Okay, so you introduce a window in the shielding.
Yes, exactly.
Okay, there is some removable part, or
well, you can open the shielding. It's in 3 parts. You can open it. Another way to do it is just to put. We have some space in the shielding next to the cryostat. You can just also put, for example, a californium source. It depends on the number of events that you are trying to see. Actually, we are right now trying to do neutron calibration. We have tested bringing a quite high neutron source, as the reactor is off right now, a quite high neutron source next to our shielding, but this hasn't gotten us very probant results. The next test that we are going to do is to put a californium source in the shielding right under the cryostat. So in this case, it's the way we would do it, but there's other techniques if the reactor is on, just to open the cryostat and see your neutrons.
Okay, thank you. That's clear.
Anyone else? I'll go. If not, I guess my one question you didn't mention much about, but it was on one of your slides. You want a timing resolution of 100 microseconds at 100 EV. How important is that for this kind of experiment? Because I mean, as I understand this, the reactor is not sort of pulsing neutrinos; it's just a continuous flux. So what does the timing resolution achieve in this particular case?
Well, it's quite specific. It's because so we have 15 meter waters equivalent of overburden, which is quite nice for this kind of experiment, but it's clearly not enough to have a very low weight of muons in our detectors, and this is why we are using a muon veto. And with a muon veto, you want to be very synchronized with your detectors to be able to say, okay, we have events that were tagged by the muon veto, and so all of the events around this tag with hopefully a very short timing resolution, we don't consider them because they are most certainly created by muons. So it's specifically a question of muon veto synchronization.
Yeah, it was the veto. Okay, that makes sense. The other thing I was curious about, so I mean, this probably is maybe a basic or a boring thing, but the diagram of your sort of detector unit, you had the ionization detectors on top and bottom, but the heat only on one side. Is there a
Yes.
reason for that?
There's no particular reason instead of design of the holders, apart from design of the holders. There actually is a way for us to put a heat sensor on the bottom, or even two heat sensors on the top and on the bottom. There's no real reason to do that for us right now, but at some point it might become interesting. That's just one thing that we can do. So there's no particular reason for it to be on top, except that it's easier to produce.
Mm-hmm. And the other thing was so you mentioned you had the planar versus the FID electrodes. Is my understanding is that you're just testing both of them. When you
Yes.
showed this slide, I thought maybe you were going to place these FID ones where it's more important to project surface events, but it seems like you basically just got these two essentially side by side.
Exactly, that's the idea. And we think that it's one of the strengths of the experiment is that to us, it's quite easy to go from one electrode design to another. And we don't want to choose from the two designs, in between the two designs, before seeing the performances of the two designs on site with the data from the reactor. And we will be able to do that and to choose if we want either all planar detectors or all FID detectors or even a mix of them in the final correction.
Oh, cool. Okay. And yeah, maybe so this I think is just very basic. Maybe there's something I'm missing. So when you showed the plot of ionization energy versus recoil energy, but of course your two observables are ionization energy and heat. So is
Yeah.
recoil energy here defined as ionization plus heat, and assuming that everything is captured?
So this is something I haven't mentioned, but there's a little difference between heat energy and recoil energy. So here, when you create electron hole pairs for the ionization and you make them drift, these electrons and holes, while they drift, they will kind of collide with the matrix, the atoms matrix of your crystal, and by some kind of a Joule effect, which is known as a Luke-Neganov-Trofimov effect, you will create some additional phonons, which will themselves thermalize into heat. So your heat signal will be boosted by this Luke-Trofimov-Neganov effect, but you can predict exactly how, and then you can come back from this boosted heat measurements to the recoil energy quite easily.
Okay,
So
that's actually an interesting point. But I think the thing I missed was even more basic than that. When you say recoil energy, you're referring to heat there, right?
No, recoil energy is really the recoil energy that is deposited in the detector, which is measured in kV. But then what is measured, what is truly measured in the detector is the heat energy that arrives to the detector. And this is a little bit different, but we can deduce the recoil energy from the heat energy from subtracting the Neganov-Trofimov effect and everything.
Okay,
but
so
yeah,
there's some sort of calibration curve that's been used, and what's plotted is the calibrated recoil energy based on the measured heat. It's not the actual raw measurement.
What curve are you talking about? Sorry.
This is basically a restatement of Kieran's point. You are not plotting the raw measurement. You're plotting some.
Yes, exactly.
You're plotting some calibrated recoil energy, which is some function of the heat.
That's exactly the case, but I wouldn't use the word calibration because it's the Neganov-Trofimov effect is very well known theoretically. We're just applying a transformation to the values of the heat energy to get the recoil energy. We just have to know at which bias we are operating our crystals to be able to apply this transformation.
Okay.
So this is maybe getting too specific now, but So you have these blobs from the germanium electron capture, which are basically the line going through where the two energies are sort of equal. I mean, they're sort of sitting on the
Yeah,
green line, right?
yeah.
But then in a later slide, when you showed I think it was some calibration measurements, and you had these two peaks, and you showed, but then in that case, you were showing ionization. I think it was a later one than this, and you had a plot for ionization and a plot for heat, and they were at the same energy.
This one?
Yeah.
Yeah.
So shouldn't
Okay.
shouldn't there be a quenching factor difference in these two things,
So as I
something like
mentioned
that?
here, it's only electronic recoils,
Yeah,
and
okay.
electronic recoils have a quenching of 1
Yeah, okay.
by definition. Well, so we have the heat and ionization at the same energy for the electronic recoils, which is what we are using to calibrate our detector. So in truth, we get these peaks at a certain number of ADUs, and we calibrate our data to get these peaks at the right positions. That's how we
But
calibrate
then
it.
is there a difference between the two variables here on this plot compared to the combined plot? Maybe
So in this case, it's ionization and heat, and in the combined plot, it's ionization and recoil energy. But apart from that, there's no difference.
but so here the recoil energy is 10 kV, but then in the other one the heat energy is also
Yes.
10 kV
So
EE. Is that?
yes. So this the difference lies in the unit. So when we plot energy in kVEE, it's for electron equivalence. So we are calibrating things so that they are at 10.37 kV, and this, by the calculations that we are making to transform everything in kV, brings them at the same energy for electronic recoils.
Yeah.
But it's not the case for nuclear recoils.
Yeah. I think that was the only thing I was missing. Yeah. Any final points from or questions?
Perhaps just a quick one about this plot since you brought it back up. So I understand that you at Ricochet have a better threshold than the Edelweiss experiment.
Yes.
But still the structure of the deposits from germanium seem quite different. It's not just that these are smaller, which they are and which is what I would expect, but this large deposit, which is a notable feature in Edelweiss, is either missing or strongly displaced. What's the reason for that?
So I mentioned that very briefly when I presented this plot for the first time, but this huge mass is just our electronic noise.
That's
When we are
noise.
triggering,
Okay.
when we are triggering on just the traces without events. Just electronic noise. And the fact that this huge mass corresponds to this huge mass here shows that we are capable of probing way lower energies because we have better resolutions and thus better thresholds.
Okay, but that's a function of the improved electronics.
Yes, of multiple things, because also in the Edelweiss experiment, the size of the detectors and the mass of the detectors weren't the same, and this has an impact specifically on the heat resolution. But if we're talking about only ionization, it's mainly a question of improved electronics and everything. Yeah.
Thank you.
Okay. Well, thanks everyone. Yeah, and thank you very much, Nicolas, for a great talk. I'm very excited to see where this goes next. And
Thank you.
thanks for taking the time to be with us. So I'll stop recording.